Tonight, we're going to explore one of the most unsettling questions in all of science. What if everything we thought we knew about being first on this planet is wrong? What if humanity isn't the first intelligent civilization Earth has produced? What if millions of years before we built our first cities, before we discovered fire, before our ancestors even existed, another species rose to dominance, built their own civilization, and then vanished so completely that we can barely detect they were ever here? By the end of tonight, you're going to understand why this isn't just science fiction, and why some of the world's leading scientists take this possibility seriously enough to have developed methods for detecting ancient civilizations in Earth's geological record. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something that should make you uncomfortable. Our species, Homo sapiens, has existed for roughly 300,000 years. For most of that time, we were nomadic hunter-gatherers, leaving almost no trace. Agriculture began about 10,000 years ago. Cities emerged around 6,000 years ago. Written records, what we call recorded history, that's only 5,000 years old. But here's the thing that should terrify you. Earth is 4.54 billion years old. Even if we count our entire 300,000-year existence as a species, that's only 0.0066% of Earth's total history. Let me put that in perspective. If Earth's entire history was compressed into a single 24-hour day, human civilization would appear in the last 0.08 seconds. Less than a tenth of a second. A blink. A fraction of a moment, so brief, it's almost nothing. Now, ask yourself this question. In all those billions of years before us, in all that incomprehensible stretch of time, is it really impossible that intelligence emerged before? That's the question at the heart of what scientists call the Silurian Hypothesis. And yes, before you ask, it's named after a race of intelligent reptiles from Doctor Who. The scientists who came up with this hypothesis have a sense of humor, but the question itself is deadly serious. The Silurian Hypothesis was formally proposed in 2018 by Gavin Schmidt and Adam Frank. Schmidt is the director of NASA's Goddard Institute for Space Studies. Frank is a professor of astrophysics at the University of Rochester. These aren't fringe figures. They're mainstream scientists asking a genuinely difficult question. How would we know if an industrial civilization existed on Earth millions of years ago? What traces would they leave? And more importantly, what traces would survive long enough for us to find? The hypothesis doesn't claim that ancient civilizations definitely existed. It asks a different question. If they did exist, could we detect them? And the answer, which surprised even the scientists who studied it, is maybe not. Depending on how long ago they existed and how long their civilization lasted, we might never find direct evidence. The Earth is remarkably good at erasing history. Let's think about what would happen to our own civilization if humanity disappeared tomorrow. Imagine every human vanishes instantly. What would remain after 1 million years? After 10 million? After 100 million? The answer is disturbing. Almost nothing. Buildings would collapse within a few hundred years as steel corrodes, concrete crumbles, and wood rots. Within 10,000 years, the great cities we've built, New York, London, Tokyo, Shanghai, would become unrecognizable mounds buried under vegetation. Give it 100,000 years, and erosion would erase our highways, dams, and airports completely. Within 1 million years, plate tectonics would take over, crushing, melting, or scattering whatever remained. And here's why this matters. We build our cities on coastal plains and river valleys, places that are constantly being reshaped by erosion. These are exactly the worst places to leave a permanent record. After 10 million years, nothing recognizable would be left. After 100 million years, the continents themselves would have shifted thousands of miles, and any physical trace of human civilization would be completely obliterated. So, if we disappeared today, and some other species evolved intelligence 100 million years from now, what evidence would they find that we existed? This is where the Silurian hypothesis gets interesting. Because Schmidt and Frank weren't just asking an idle question, they were thinking about how we search for evidence of past civilizations. They were thinking about what markers might survive geological timescales. And they were thinking about this in the context of another problem entirely: detecting industrial civilizations on other planets. If we can't even be sure we detect an ancient industrial civilization on our own planet, how can we possibly hope to detect one on a planet orbiting another star millions of light years away? The key insight of the Silurian hypothesis is that we need to look for indirect markers, not buildings or artifacts, but chemical and isotopic signatures, changes in the geological record that indicate something unusual was happening. Let's talk about what those markers might be. And let's be thorough about this, because understanding these markers is crucial to understanding why ancient civilizations might be undetectable. When Schmidt and Frank published their paper, they weren't just speculating. They did the math. They calculated what traces our current industrial civilization would leave in the geological record. They looked at every possible marker they could think of. And then they worked backward, asking what those same markers would look like millions of years from now. The results were sobering. First, there's the spike in carbon dioxide. Our current industrial civilization has increased atmospheric carbon dioxide from about 280 parts per million before the Industrial Revolution to over 420 parts per million today. That's a massive increase in a geological blink of an eye, just over 250 years, to add more than 140 parts per million. To put that in perspective, the natural variation in carbon dioxide over the past 800,000 years, measured from ice cores in Antarctica, has been between about 180 and 300 parts per million. We've pushed it 50% higher than any point in the last 800,000 years. And we did it in less time than it takes a sequoia tree to grow. This leaves a signature in the geological record because carbon dioxide affects the chemistry of the ocean, which affects what gets deposited as sediment, which eventually becomes rock. Here's how it works. Carbon dioxide dissolves in ocean water, forming carbonic acid. This lowers the pH of the ocean, making it more acidic. More acidic water dissolves calcium carbonate, the material that many sea creatures use to build their shells and skeletons. Corals, mollusks, certain types of plankton, all of them struggle in acidic water. When these organisms die and settle to the ocean floor, they normally form thick layers of calcium carbonate sediment. Over millions of years, these layers compress and lithify into limestone. Limestone is one of the most common sedimentary rocks on Earth. The White Cliffs of Dover in England are limestone, formed from the shells of countless tiny marine organisms that lived in ancient seas. But when the ocean becomes more acidic, less calcium carbonate gets deposited. The shells dissolve before they can accumulate. The sediment that forms contains less carbonate and more clay or silica. So, if you drill a core through ocean sediments and you see a sudden shift from carbonate-rich layers to carbonate-poor layers, that tells you something changed in the ocean chemistry. And if you see that shift happen very quickly, over just a few thousand years or less, that tells you the change was abrupt. Our current industrial carbon dioxide release would create exactly this signature. A sharp boundary in the sediment where carbonate-rich layers give way to carbonate-poor layers. Future geologists would see this and know something dramatic happened, but that's not all. Carbon itself comes in different isotopes. Most carbon is carbon-12, which has 6 protons and 6 neutrons. But about 1% of natural carbon is carbon-13, which has an extra neutron, and a tiny fraction is carbon-14, which is radioactive and decays over thousands of years. When plants photosynthesize, they preferentially use carbon-12 because it's lighter. So plant tissue ends up slightly depleted in carbon-13 compared to atmospheric carbon dioxide. This is called isotopic fractionation. Fossil fuels, coal, oil, and natural gas are made from ancient plant material, so they're depleted in carbon-13. When we burn fossil fuels, we're releasing carbon that's isotopically light, that has a lower ratio of carbon-13 to carbon-12 than average. This changes the isotopic ratio of carbon dioxide in the atmosphere. And that change gets recorded in sediments. Organisms that build shells from dissolved carbon dioxide in the ocean incorporate the carbon with whatever isotopic ratio was present at the time. So, if you measure the carbon isotope ratio in fossil shells from different time periods, you can reconstruct how atmospheric carbon dioxide isotopic composition has changed. Our industrial activity is creating a distinct isotopic signature. The carbon-13 to carbon-12 ratio is dropping because we're adding so much isotopically light carbon from fossil fuels. This signature would be detectable in the geological record for millions of years. Long after the physical artifacts of our civilization have vanished, the isotopic evidence would remain. Future geologists examining rock layers from our time would see a sharp spike in carbon dioxide, inferred from the chemistry of the sediments. They'd see ocean acidification, inferred from the lack of carbonate. They'd see an isotopic shift toward lighter carbon, indicating a massive input of organic carbon. All of this would be anomalous compared to the baseline. It would stand out. But here's the problem. We see similar spikes in Earth's past, rapid increases in atmospheric carbon dioxide, ocean acidification events. Global warming episodes that happened far too quickly to be explained by normal geological processes. The Paleocene-Eocene thermal maximum, which happened about 56 million years ago, saw global temperatures rise by 5 to 8 degrees Celsius in just a few thousand years. Maybe as little as 20,000 years, which is an eye blink geologically. Carbon isotope ratios shifted dramatically. Ocean chemistry changed rapidly. Carbonate deposition decreased. The deep ocean became oxygen poor, a condition called anoxia. Many species of deep-sea organisms went extinct. It looks, in some ways, remarkably similar to what we're doing to the planet right now. Now, scientists have explanations for the Paleocene-Eocene thermal maximum that don't require ancient civilizations. The leading hypothesis involves massive volcanic eruptions in the North Atlantic, where Greenland and Europe were splitting apart as the continents drifted. These eruptions released vast amounts of carbon dioxide over tens of thousands of years. The warming then triggered the destabilization of methane hydrates on the ocean floor. Methane hydrates are ice-like solids made of methane trapped in a cage of water molecules. They're stable in cold, high-pressure conditions, like the deep ocean floor. But if the ocean warms, the hydrates become unstable and release their methane. Methane is a greenhouse gas, much more potent than carbon dioxide, so this release causes more warming, which destabilizes more hydrates, creating a runaway feedback loop. Eventually, the methane oxidizes to carbon dioxide, adding even more greenhouse gas to the atmosphere. The result is rapid, catastrophic warming. This is a good explanation. It fits the evidence. We can see the volcanic rocks from that period. We can calculate how much carbon dioxide the eruptions would have released. We can model the methane hydrate destabilization. It all works. But here's the unsettling question the Silurian Hypothesis asks. How would we know the difference between this volcanic scenario and an industrial civilization that collapsed after depleting its resources and triggering runaway climate change? Both would show rapid carbon release. Both would show ocean acidification. Both would show isotopic shifts toward lighter carbon, because both fossil fuels and methane are depleted in carbon-13. Both would show global warming. Both would show mass extinction, particularly of marine species sensitive to acidification and oxygen depletion. The main difference is that volcanism leaves volcanic rocks. Thick layers of basalt, volcanic ash, distinctive minerals that form in volcanic environments. But industrial activity might also leave markers we're not recognizing. Unusual metal distributions, for instance. Industrial civilization concentrates metals in specific locations, cities, manufacturing centers, waste sites. When those cities erode and wash into the ocean, those metals go with them. Or, consider the nitrogen cycle. Modern agriculture uses massive amounts of synthetic nitrogen fertilizer. We produce about 150 million tons of it every year. This is created through the Haber-Bosch process, which takes nitrogen from the air and combines it with hydrogen to make ammonia. The process uses enormous amounts of energy, mostly from burning natural gas, and it has a specific isotopic signature. Atmospheric nitrogen is mostly nitrogen-14, with a small fraction of nitrogen-15. The Haber-Bosch process doesn't fractionate isotopes significantly, so the fertilizer has roughly the same ratio as atmospheric nitrogen. But when that fertilizer gets applied to fields, used by crops, and then washed into rivers and oceans, it changes the nitrogen isotope ratio in marine sediments compared to natural biological nitrogen fixation. Natural nitrogen fixation, done by bacteria in soil and water, does fractionate isotopes. The fixed nitrogen ends up slightly enriched in nitrogen-14. So if you see a shift in the nitrogen isotope ratio in sediments toward values closer to atmospheric nitrogen, that could indicate industrial fertilizer use. This is subtle. It requires very careful measurement, but it's potentially detectable. Future geologists would need to be looking for it specifically, and they'd need to understand what it meant. If they're not asking whether ancient civilizations could have existed, they might see the anomaly and explain it with some natural process. Unusual upwelling patterns bringing deep ocean nitrogen to the surface. A change in the bacterial community doing nitrogen fixation. Something. The point is, the signatures are ambiguous. They could have natural explanations, but they could also have industrial explanations. And after tens of millions of years of geological processing, telling them apart becomes nearly impossible. The second marker is nitrogen isotopes. Modern agriculture uses massive amounts of synthetic nitrogen fertilizer. We produce this through the Haber-Bosch process, which fixes atmospheric nitrogen into ammonia. This process has specific isotopic signatures. It preferentially uses certain isotopes of nitrogen, leaving traces that might, potentially, be detectable in the geological record. But again, we see anomalous nitrogen signatures in ancient rocks. Are these the result of natural biological processes, unusual ocean chemistry? Or could some of them be industrial signatures we don't recognize? Third, there's plastic. Modern civilization produces hundreds of millions of tons of plastic every year. About 380 million tons in 2020. Since mass production began in the 1950s, we've created over 8 billion tons of plastic. Much of this plastic ends up in the ocean, where it breaks down into microplastics that work their way into sediments. Microplastics are everywhere now, in the deepest ocean trenches, in Arctic ice, in the guts of fish and seabirds, in human blood and lungs. They're inescapable. Plastic is made from petroleum, from ancient organic matter that's been buried and heated and pressured for millions of years. It contains specific chemical signatures that don't occur in nature. Long-chain polymers of hydrocarbons arranged in patterns that biology doesn't create. Polyethylene, the most common plastic, is just a long chain of carbon atoms with hydrogen attached. Chemically simple, but the chains are thousands of units long, far longer than anything biological processes create. Polystyrene, another common plastic, has benzene rings attached to the carbon chain. Again, not something you find in nature in this form. PVC, polyvinyl chloride, contains chlorine atoms in the polymer chain. Teflon contains fluorine. These aren't just organic compounds. They're specific synthetic molecules that require industrial processes to create. They're signatures of technology. If a geologist 100 million years from now drilled a core through sedimentary rock and found a layer absolutely saturated with tiny plastic particles, all dating to the same narrow time period, that would be a pretty strong signal that something unusual was happening. But would that layer survive? Plastic degrades. Slowly. But it does degrade. UV light from the sun breaks down plastics on the surface. Oxygen causes oxidation that weakens the polymer chains. Microbes are evolving to eat plastic. Enzymes that can break down the long chains into shorter fragments that can be metabolized. In 2016, Japanese researchers discovered a bacterium, Ideonella sakaiensis, that had evolved the ability to break down PET plastic, polyethylene terephthalate, the kind used in water bottles. The bacterium produces an enzyme that cleaves the polymer chains. This was remarkable because PET has only existed in large quantities since the 1970s. In just 40 years, bacteria had evolved to eat it. Other organisms are following suit. Fungi that can break down polyurethane. Worms that can digest polyethylene. Evolution is responding to this new food source. Given enough time, millions of years, plastic might be completely biodegradable. The microbes would become more efficient. They'd spread worldwide. They'd consume the plastic, breaking it down into carbon dioxide, water, and biomass. So the 8 billion tons of plastic we've created might not leave a permanent marker. It might all get eaten. But even if the plastic degrades, it might leave traces, chemical markers in the sediment, unusual ratios of organic compounds, patterns of carbon isotopes that indicate synthetic polymers were present. These would be subtle, A geochemist would need to be looking specifically for them. They'd need to run sophisticated analyses, mass spectrometry to identify unusual molecular fragments, isotopic analysis to detect synthetic signatures. And they'd need to be asking the right questions. If they're assuming all organic matter in sediments is natural, they might not investigate closely enough to find the anomalies. There's also the question of where plastic accumulates. Most of it ends up in the ocean. Some sinks to the bottom and gets buried in sediments. Some washes up on beaches and gets buried there. Some gets subducted as ocean crust slides under continental plates. Subducted material gets heated and pressured and eventually melts, becoming magma that rises to form volcanoes. Any plastic in that material would be completely destroyed, broken down into simple molecules, carbon dioxide, water, maybe some chlorine and fluorine gases, if it was PVC, polyvinyl chloride, or Teflon. So plastic that enters subduction zones wouldn't leave a marker. It would vanish. But plastic, buried in stable sediments, on continental shelves, or in deep ocean basins that aren't subducting, might be preserved. At least for a while. Heat and pressure over millions of years would transform it. The long polymer chains would break. The complex molecules would simplify. Eventually, it would become indistinguishable from other organic matter in the sediment. After 100 million years, would enough remain to be detectable? Maybe, maybe not. It depends on the burial conditions, on the temperature and pressure history, on whether microbes reached it before it was too deeply buried, on whether the sediments remained stable or were disturbed by geological processes. There are too many variables to say for certain. But the fact that we can't say for certain, that's the point. We don't know what would survive and what wouldn't. We're guessing. And if we're guessing about our own civilization, one we understand intimately, how can we possibly be confident about detecting civilizations from millions of years ago? Fourth, there's radioactive isotopes. Nuclear weapons testing in the 1940s and 1950s released radioactive isotopes into the atmosphere that have now settled into sediments worldwide. Plutonium-239, cesium-137, strontium-90, carbon-14, tritium. These isotopes don't occur naturally in significant quantities. They're smoking guns. Definitive proof of nuclear technology. Let's talk about plutonium-239, specifically because it's the most distinctive signature. Plutonium doesn't exist in nature except in trace amounts from natural nuclear reactors that operated billions of years ago. Natural uranium deposits, under very specific conditions, can become critical and sustain a chain reaction. This happened at Oklo, in Gabon, Africa, about 2 billion years ago. Groundwater acted as a moderator, slowing neutrons enough to sustain fission in rich uranium ore. But those natural reactors shut down billions of years ago. And they produced only tiny amounts of plutonium, far too little to detect in modern sediments. All the plutonium in the environment today comes from human activity, nuclear weapons testing, plutonium production in reactors, nuclear accidents like Chernobyl and Fukushima. The peak of atmospheric nuclear testing was in the early 1960s, before the Limited Test Ban Treaty of 1963 banned atmospheric tests. The United States, Soviet Union, United Kingdom, France, and China detonated over 500 nuclear weapons in the atmosphere. Each detonation created a mushroom cloud that lifted radioactive debris into the stratosphere. This debris circulated globally, eventually falling back to Earth over months and years. By the mid-1960s, you could detect plutonium-239 in soils and sediments everywhere on Earth. Antarctica, the Arctic, remote islands, deep ocean sediments, everywhere. The concentration isn't high. We're talking about incredibly small amounts, measured in becquerels per kilogram or atoms per gram. But it's there, and it's globally distributed. This creates a marker horizon in sediments, a thin layer, corresponding to the early 1960s, with elevated plutonium levels. Geologists already use this as a stratigraphic marker. When they drill sediment cores from lakes or ocean floors, they can identify the 1960s layer by measuring plutonium. It helps them date the sediments. Everything below that layer is older than 1963. Everything above is younger. Now, if a geologist 1 million years from now found this layer, what would they conclude? First, they'd need incredibly sensitive instruments to detect it, because plutonium-239 decays. Radioactive decay is exponential. Each isotope has a half-life, the time it takes for half of it to decay. Plutonium-239 has a half-life of 24,100 years. After one half-life, 24,100 years, half of the original plutonium has decayed into uranium-235 and other products. After two half-lives, 48,200 years, only 1/4 remains. After three half-lives, 72,300 years, 1/8 remains. The equation is simple: exponential decay. Amount remaining equals initial amount times 1/2 to the power of time divided by half-life. After 1 million years, that's about 41.5 half-lives. The amount remaining becomes vanishingly small. If you started with 1 kilogram of plutonium-239, after 1 million years, you'd have less than a trillionth of a gram left. Essentially, undetectable. That's not detectable. You'd need to measure individual atoms, and even then, you'd be looking for a handful of atoms in a kilogram of sediment. It's below any realistic detection limit. After 10 million years, you'd have less than 1 atom per kilogram. After 100 million years, forget it. There would be absolutely nothing left. So plutonium signatures are definitive proof of nuclear technology, but they only last a few million years. Maybe 10 million at the absolute maximum, with perfect preservation and incredibly sensitive detection. After that, they're gone, completely erased by radioactive decay. Other nuclear isotopes have even shorter half-lives. Cesium-137, which was released in large quantities at Chernobyl, has a half-life of about 30 years. After 1,000 years, it's undetectable. Strontium-90 has a half-life of about 29 years. Same story. Carbon-14, which is produced in large quantities in nuclear reactors and was also released by atmospheric testing, has a half-life of 5,730 years. After 50,000 years, it's gone. Tritium, radioactive hydrogen, with a half-life of about 12 years, vanishes even faster. So the nuclear signatures we're creating won't last. They're temporary markers, visible for thousands to maybe millions of years, but not longer. If a civilization existed 50 million years ago and they had nuclear technology, we'd never find the evidence. It would have decayed to nothing. The only nuclear signature that might last longer is changes in the isotopic ratios of uranium and thorium in certain environments. When uranium undergoes fission in a nuclear reactor, It splits into two smaller atoms plus neutrons. The smaller atoms are fission products, things like cesium, strontium, iodine, xenon, dozens of different elements. These fission products have different isotopic ratios than naturally occurring elements. They're enriched in certain isotopes that are rare in nature. If you found an ancient nuclear reactor site, even after the short-lived isotopes had decayed, you might still detect anomalous isotopic ratios in certain elements. But this requires finding the actual reactor site, which is incredibly unlikely, and you'd need to distinguish between artificial reactors and natural reactors like Oklo. It's possible, but not easy. The bottom line is that nuclear signatures are the most definitive marker of industrial civilization, but they're also the most temporary. They don't survive geological timescales. So we have this paradox. The clearest evidence of technology is also the evidence that vanishes fastest. Fifth, there's unusual metal concentrations. Industrial civilization mines metals from the earth and concentrates them in specific locations. Cities are essentially massive deposits of concentrated iron, copper, aluminum, rare earth elements. When those cities erode and wash into the ocean, those metals go with them. They create anomalous sediment layers with much higher metal concentrations than you'd normally see. We do see anomalous metal layers in ancient sediments. The iridium layer at the Cretaceous-Paleogene boundary, the event that killed the dinosaurs 66 million years ago, is one example. But we can explain that with an asteroid impact. Asteroids are rich in iridium, so a large impact would deposit a global layer of iridium-rich dust. The question is, are there other anomalous metal layers that we can't easily explain? And if there are, how do we tell whether they came from geological processes or from ancient industrial activity? Sixth, and this is perhaps the most intriguing, there's the possibility of fossilized structures, not buildings. Those wouldn't last, but tunnels, mines, deep excavations, things that were buried quickly and protected from erosion. Modern civilization has created vast underground networks, subway systems, utility tunnels, mine shafts extending miles into the earth. Some of these might, under very specific circumstances, be preserved in the geological record. Imagine a mine shaft that collapsed and was immediately filled with sediment, then buried under more sediment, then compressed into rock over millions of years. A geologist examining that rock millions of years later might find a peculiar cylindrical cavity extending deep underground, far deeper than any natural cave system, with unusual geometry. They might find tool marks on the walls, though after enough time and pressure, even those would be smoothed away. They might find it suspicious, but could they prove it was artificial? Probably not. The seventh marker, and this is more speculative, is changes in biodiversity. Industrial civilization is currently causing what many scientists call the sixth mass extinction. Species are dying at rates 100 to 1,000 times higher than the natural background extinction rate. This will leave a mark in the fossil record. A sudden, dramatic decrease in the number of species, concentrated in a very narrow time window. We do see extinction events in Earth's past. The Permian-Triassic extinction, 252 million years ago, killed about 96% of all marine species and 70% of terrestrial vertebrate species. The Cretaceous-Paleogene extinction, 66 million years ago, killed the non-avian dinosaurs and about 75% of all species. These events have explanations. massive volcanic eruptions. Asteroid impacts. Runaway climate change. But here's the question. If we saw an extinction event that we couldn't easily explain with volcanism or impacts, an event that coincided with spikes in carbon dioxide, unusual metal concentrations, and other anomalies, would we consider the possibility that it was caused by an ancient civilization? Or would we simply invent a natural explanation and move on? This is one of the key insights of the Silurian hypothesis. We might be looking at evidence of ancient civilizations and not recognizing it because we're not asking the right questions. We're assuming that all anomalies in the geological record have natural explanations because we've never seriously considered the alternative. Now, before we go further, let me be absolutely clear about something. There is currently no convincing evidence that an ancient industrial civilization existed on Earth. None. The anomalies we see in the geological record all have plausible natural explanations. The Silurian hypothesis doesn't claim ancient civilizations existed. It asks how we would know if they did, and it points out that our current methods might not be sufficient to detect them. The value of the hypothesis isn't that it proves ancient civilizations existed. The value is that it forces us to think carefully about what kinds of evidence would survive geological timescales. And that has implications far beyond Earth. Because if we're looking for evidence of civilizations on other planets, we need to know what to look for. And if civilizations don't leave permanent markers, if evidence degrades over millions of years, then we might be looking at planets that once hosted advanced civilizations and not recognizing them. Let's think about the time scales involved here, because they're absolutely crucial. Life on Earth is approximately 3.7 billion years old. Single-celled organisms appeared almost as soon as the planet cooled enough to support liquid water. But those single cells remained single cells for a very long time. Complex multicellular life didn't appear until about 600 million years ago. That's 3 billion years of nothing but microbes. The first animals appeared in the Cambrian explosion about 540 million years ago. Fish appeared about 500 million years ago. The first land plants appeared about 470 million years ago. The first land animals, primitive arthropods and amphibians, appeared about 400 million years ago. Dinosaurs appeared about 230 million years ago and dominated for 165 million years before being wiped out 66 million years ago. Mammals were around during the time of the dinosaurs, but they were small, mostly nocturnal creatures living in the shadows of the great reptiles. After the dinosaurs died, mammals diversified rapidly. Primates appeared about 60 million years ago. The evolutionary line leading to humans split from chimpanzees about 6 million years ago. The genus Homo, our genus, appeared about 2.8 million years ago. Anatomically modern humans appeared about 300,000 years ago. Civilization appeared about 10,000 years ago. Industrial civilization appeared about 250 years ago. Look at those numbers. From the first appearance of complex life to now is 540 million years. Industrial civilization has existed for 250 years. That's 0.0000046% of the time complex life has existed. Now, the question the Silurian hypothesis asks is this. In those 540 million years, is it really impossible that some other species developed intelligence and industry? Most people's immediate reaction is, yes, it's impossible. We'd know. We'd have found their cities, their artifacts, their technology. But would we? Here's a thought experiment. Imagine an intelligent species evolved on Earth 200 million years ago. Call them the Silurians, just for convenience. They weren't mammals. Maybe they were highly intelligent dinosaurs, or something else entirely. They evolved complex brains. They developed tool use. They discovered fire. Over hundreds of thousands of years, they built a civilization. This civilization lasted for, let's say, 100,000 years. That's 20 times longer than human civilization has existed. Long enough to develop agriculture, writing, mathematics, science, industry. Long enough to build cities, smelt metals, burn fossil fuels, create plastic, split the atom. Then, something happened. Maybe they destroyed themselves in a nuclear war. Maybe a disease wiped them out. Maybe they damaged their environment so badly that their population crashed. Maybe an asteroid hit. Or maybe they just went extinct, naturally. The way 99.9% of all species that have ever existed have gone extinct. Their civilization ended. Their cities crumbled. Their technology corroded. The Earth, indifferent and patient, buried everything under layer after layer of sediment. 200 million years pass. Continents drift. Mountains rise and erode. Ocean basins open and close. The Silurians' homeland might now be at the bottom of the Atlantic Ocean, subducted beneath the European plate. Or it might be at the top of the Himalayas, thrust upward by the collision of India and Asia. What would remain? What could we possibly find? The answer depends on where we look and what we're looking for. If we drilled a core through sedimentary rock dating to 200 million years ago and analyzed it very carefully, we might find anomalies. A spike in carbon isotopes, unusual metal concentrations, a small extinction event, changes in pollen indicating rapid deforestation. But we'd probably interpret these as natural events. A period of volcanism, an asteroid impact, a climate fluctuation. We wouldn't think ancient civilization because we're not trained to think that way. We don't have a framework for recognizing industrial signatures in very old rocks. And here's the really disturbing part. We might have already found evidence and dismissed it. The geological record is full of anomalies we don't fully understand, events that happen too quickly, isotope ratios that don't quite make sense, extinction pulses with unclear causes. Most of these have proposed natural explanations. But those explanations are sometimes speculative, sometimes incomplete. We accept them because they're more plausible than the alternative. And the alternative, ancient civilizations, seems so absurd that we don't seriously consider it. But maybe we should. Not because ancient civilizations definitely existed, but because if they did exist, this is exactly what the evidence would look like. Ambiguous, open to interpretation, indistinguishable from certain natural processes. The Silurian hypothesis forces us to confront an uncomfortable truth. The absence of evidence is not evidence of absence. Just because we haven't found definitive proof of ancient civilizations doesn't mean they didn't exist. It might just mean we're not capable of detecting them. Now, let's think about this from a different angle. What are the requirements for intelligence to evolve? Surprisingly, intelligence is not particularly common in Earth's history. Billions of species have existed. Millions of species exist today, but only one has developed civilization. Only one has created technology, built cities, written books, done science. Why? Intelligence is expensive. Brains use enormous amounts of energy. The human brain is about 2% of body weight, but uses about 20% of the body's energy. That's a massive investment. Evolution only makes that investment if it pays off. For most species, intelligence doesn't pay off. A deer doesn't need to do calculus. It needs to run fast and avoid predators. A shark doesn't need to build tools. It needs sharp teeth and efficient swimming. Intelligence is useful primarily when an animal needs to solve novel problems, when the environment is complex and changing, when social dynamics are complicated, when tool use provides survival advantages. Primates evolved high intelligence, partly because they live in complex social groups where understanding relationships, remembering favors, detecting deception, all provide advantages, partly because they live in varied environments requiring flexibility, and partly because their hand anatomy allows sophisticated tool use, creating a feedback loop where better brains allow better tools which reward even better brains. But there's no reason primates should be the only group capable of this. Octopuses are highly intelligent. They solve problems, use tools, demonstrate planning and memory. But they're solitary and short-lived, so their intelligence doesn't accumulate culturally. Each octopus learns largely from scratch. Dolphins and whales are highly intelligent. They have complex social structures, communication systems, culture, but they lack hands. They can't build tools. They can't control fire. Their intelligence can't lead to technology. Crows and parrots are remarkably intelligent for their brain size. They use tools, solve multi-step problems, demonstrate causal reasoning, but they're small. Their brains are small. There are limits to what a brain that weighs 30 grams can accomplish. So, the requirements for a species to develop civilization seem to be long lifespan for cultural accumulation, social structure for cooperation and knowledge transfer, manipulative appendages for tool use, sufficient brain size for complex reasoning, environmental pressure to reward intelligence, and time, millions of years for evolution to shape behavior and anatomy. Humans meet all these requirements, but we're not obviously unique in that regard. Dinosaurs existed for 165 million years. That's 33 times longer than mammals have been dominant. In all that time, did none of them evolve these traits? The traditional answer is no. Dinosaurs are portrayed as big, dumb reptiles. All muscle and teeth, no brains. But that's increasingly recognized as wrong. Many dinosaurs, particularly theropods, the group that includes Tyrannosaurus and Velociraptor, had large brains relative to their body size. Some were probably as intelligent as modern birds, which makes sense because birds are dinosaurs. They're the surviving lineage. Let's dig into this, because it's crucial to understanding whether dinosaurs could have evolved intelligence. Brain size matters, but it's not everything. What really matters is the ratio of brain size to body size, called the encephalization quotient, or EQ. Humans have an EQ of about 7. That means our brain is 7 times larger than you'd expect for a mammal of our body size. Chimpanzees have an EQ of about 2.5, dolphins about 4, elephants about 1.9. Most mammals have an EQ around 1, which is the baseline. Larger mammals tend to have larger absolute brain sizes, but their EQ stays around 1 because their bodies are scaling up proportionally. Now, measuring dinosaur EQ is tricky because we don't have their brains. We have their skulls. We can measure the volume of the brain case, the cavity in the skull where the brain sat. But the brain didn't fill the entire cavity. There was cerebrospinal fluid, blood vessels, protective membranes. So we estimate brain size as maybe 60 to 70% of brain case volume. Then we estimate body mass from skeletal measurements. Then we calculate EQ. It's imprecise, but it gives us a rough idea. Most large dinosaurs had very low EQs. Sauropods, the giant long-necked herbivores like Brachiosaurus and Diplodocus, had EQs around 0.2 to 0.3. Their brains were tiny compared to their enormous bodies. This makes sense. You don't need a huge brain to eat plants and avoid predators when you're 50 tons and covered in armored skin. Your main challenge is eating enough food to fuel your massive body, not solving complex problems. But theropods, the carnivorous dinosaurs, are different. Predators generally need more brain power than herbivores. They need to track prey, plan ambushes, coordinate with pack members, remember locations and behaviors. It's cognitively demanding. Large theropods, like Tyrannosaurus rex, had EQs around 2. Not spectacular, but respectable, similar to modern crocodiles. But some smaller theropods had much higher EQs. Troodon, which I mentioned earlier, lived in the late Cretaceous, about 75 to 65 million years ago, right before the asteroid impact. Troodon was about 2 meters long, about 6.5 feet, including its tail. It weighed maybe 50 kilograms, about 110 pounds, about the size of a large dog. Its brain case indicates an EQ of about 5.8. That's in the range of modern parrots and crows, among the most intelligent birds. Troodon had large eyes with forward-facing sockets, suggesting stereoscopic vision and good depth perception. Its hands had partially opposable digits with sharp claws, useful for grasping. Its teeth were small and serrated, suggesting it might have been omnivorous, eating a varied diet of small animals, eggs, insects, maybe even plants. Some paleontologists, notably Dale Russell in the 1980s, speculated about what might have evolved from Troodon if the asteroid hadn't hit. Russell created a model called the dinosauroid, a hypothetical intelligent dinosaur descended from Troodon. The model was controversial. It looked remarkably humanoid, with an upright posture, large head, forward-facing eyes, manipulative hands. Critics pointed out that Russell was making too many assumptions about convergent evolution, assuming that intelligence would necessarily lead to a human-like body plan. But the basic idea that Troodon had the potential to evolve higher intelligence isn't absurd. Birds, which are dinosaurs, have evolved remarkable intelligence. Crows can use tools, solve multi-step problems, understand cause and effect, even demonstrate theory of mind, the ability to understand that other individuals have their own thoughts and intentions. Parrots can learn human language, not just mimicking sounds, but understanding the meaning of words and combining them in novel ways. African grey parrots have been shown to have cognitive abilities comparable to a 5-year-old human child in some domains. This intelligence evolved in brains that weigh about 10 to 15 grams. Tiny compared to human brains, which weigh about 1,350 grams. The difference is neural density. Bird brains pack neurons much more densely than mammal brains. They have more neurons per gram of brain tissue. So intelligence doesn't require a huge brain. It requires the right kind of brain, with enough neurons arranged in the right structures. Troodon's brain was much larger than a crow's brain. maybe 250 to 300 grams. If it had similar neural density to modern birds, which is plausible, since it was closely related to the ancestors of birds, it could have had a very substantial number of neurons. Maybe not human level, but certainly enough for complex cognition. Now, would Trudon, or something like it, have developed civilization? That's a much bigger question. Intelligence is necessary, but not sufficient for civilization. You also need social structure, cultural transmission, environmental pressure, and time. We don't know if Trudon was social. Its teeth and skeleton suggest it might have been a pack hunter, like Velociraptor, but the fossil evidence is sparse. We've found isolated individuals, not clear evidence of group behavior. We don't know if it cared for its young or taught them skills. Some dinosaurs clearly did care for their young. We have evidence of nesting sites and parental care in some species. But for Trudon specifically, we're guessing. And Trudon went extinct in the asteroid impact 65 million years ago. The lineage only existed for about 10 million years, maybe less. 10 million years is a long time for evolution. Modern humans evolved from ape-like ancestors in about 6 million years. So it's theoretically enough time. But evolution doesn't follow a predetermined path. There's no guarantee that intelligence would have increased. Trudon might have stayed at the same cognitive level, or even decreased if environmental pressures changed. The point is, we can't say it was impossible. The anatomical prerequisites were there: large, relative brain size, stereoscopic vision, manipulative hands, potentially social behavior. Over 10 million years, over hundreds of thousands of generations, with the right environmental pressures, could Trudon, or a descendant species, have evolved human-level intelligence? Maybe. And if they had, if they'd developed tool use, language, culture, and eventually technology, what would remain after 65 million years? Almost nothing. The asteroid impact that ended the Cretaceous would have destroyed any cities or structures they built. The impact generated earthquakes, tsunamis, wildfires. It threw so much dust into the atmosphere that the planet was dark for months or years, disrupting photosynthesis and collapsing food chains. About 75% of all species went extinct. An intelligent dinosaur civilization, if it existed, would have been wiped out along with everything else. And then, 65 million years of geological processing would have erased the traces. Continents have shifted. The Atlantic Ocean has widened. India has collided with Asia, creating the Himalayas. Entire ocean basins have opened and closed. Where North America was in the late Cretaceous is not exactly where it is now. The coastlines were different. The climate was different. Most of the sediments from that period are now buried under miles of younger rock or have been subducted into the mantle. If intelligent dinosaurs built cities on the late Cretaceous coastline, those cities are now either at the bottom of the ocean or ground to dust by tectonic forces. We'd never find them. The only traces might be chemical. Carbon isotope anomalies, metal concentrations, unusual nitrogen ratios. But after 65 million years, those signals would be weak. And they'd be overwhelmed by the signals from the asteroid impact itself. The impact left a clear marker in the geological record. A global layer of iridium, an element rare on Earth, but common in asteroids. A layer of shocked quartz, formed by the intense pressure of the impact. Spherules, tiny glassy beads formed from molten rock thrown into the atmosphere. Soot, from global wildfires. All of this creates a distinctive boundary layer between Cretaceous rocks below and Paleogene rocks above. Any chemical signatures from a hypothetical dinosaur civilization would be in that same layer, mixed in with all the impact signatures. Teasing them apart would be nearly impossible. So we're left with uncertainty. Could intelligent dinosaurs have existed? The biological prerequisites were there, so it's not impossible. Would we have found evidence if they had existed? Probably not, given the time that's passed and the catastrophic end of the Cretaceous. Does absence of evidence prove they didn't exist? No, it just means we can't detect them. This is the core insight of the Silurian Hypothesis. Now, let's broaden this out. Troodon is just one example. The theropod lineage, the carnivorous dinosaurs, existed for about 150 million years before the asteroid impact. During that time, thousands of species evolved, lived, and went extinct. We've found fossils from maybe a few hundred of those species. That's a tiny fraction. Most species never fossilize. Fossilization requires very specific conditions. The organism has to die in a place where it gets buried quickly in sediment. The sediment has to be the right chemistry to preserve bone. The rock has to avoid being metamorphosed or eroded for millions of years. And then someone has to find it. The vast majority of organisms that have ever lived left no fossil record at all. So when we say we haven't found evidence of intelligent dinosaurs, what we really mean is we haven't found it in the tiny, fragmentary, incomplete fossil record we have access to. It's like looking at a book where 99% of the pages are missing and saying, "Well, I don't see any mention of this topic, so it must not be in the book." Maybe it's not. But maybe it was on one of the missing pages. And the longer ago something happened, the more pages are missing. For the early Mesozoic, the Triassic, and early Jurassic, 200 to 150 million years ago, our fossil record is even more fragmentary than for the late Cretaceous. Entire ecosystems from that time are unknown. Could intelligent dinosaurs have evolved in the Jurassic, built a civilization, and gone extinct before the Cretaceous even began? We'd never know. The fossil record from 180 million years ago is so sparse that we're constantly finding new species, reclassifying old ones, revising our understanding of what ecosystems looked like. An intelligent species that existed for even a few million years might have left a dozen fossilizable individuals. Most of those wouldn't have fossilized. Of the ones that did, most wouldn't have been preserved. Of the ones that were preserved, most haven't been found. We might have one or two incomplete skeletons sitting in a drawer in a museum somewhere, catalogued as some obscure theropod species, with no one realizing they came from an intelligent animal. Because how would you tell? Intelligence doesn't leave obvious marks on bones. You can measure brain case size, but that's imprecise. You can look at eye sockets and infer visual acuity. You can examine hand bones and see if they're suitable for manipulation. But none of that definitively proves intelligence. Modern humans and Homo erectus have similar skeletons. If all you had were bones, you might not realize that Homo sapiens built cities and wrote symphonies, while Homo erectus made simple stone tools and lived in small bands. The behavioral complexity isn't visible in the bones. So we're left in this strange position. Logically, we can't rule out that intelligent dinosaurs existed. The time frame was sufficient. 165 million years. The biological capacity was there, demonstrated by modern birds. The evolutionary opportunity existed. Complex ecosystems with selective pressures that could favor intelligence. But we have no direct evidence. And given the limitations of the fossil record and the geological erasure of history, we probably never will have direct evidence, even if intelligent dinosaurs did exist. That's unsettling. It means our understanding of Earth's history might be fundamentally incomplete. Not just in the details, but in major questions like, has intelligence emerged more than once on this planet? We can't answer that with certainty. All we can say is, not that we know of, which is a very different thing from, no, definitely not. If a dinosaur civilization existed 90 million years ago and lasted for 50,000 years, what would remain? After 90 million years of plate tectonics, erosion, sediment deposition, volcanism, everything would be gone. Absolutely gone. The continents have completely rearranged themselves since 90 million years ago. The Atlantic Ocean was narrower. India hadn't yet collided with Asia. The Himalayas didn't exist. Any cities would have been ground to powder. Any artifacts would have corroded. Any fossils of the dinosaurs themselves would be incredibly rare because fossilization is a rare process requiring specific conditions. We have thousands of dinosaur species in the fossil record, but that record is incredibly incomplete. We estimate that we've found fossils from less than 1% of all dinosaur species that existed, maybe far less than 1%. Individual species might exist for 1 million years and never leave a single fossil we've discovered. So if intelligent dinosaurs existed, if they were rare, if they existed for a geologically brief period, we would never find their fossilized bones, and we certainly wouldn't find their cities or technology. The only way we might detect them is through chemical signatures in sediments. And as we've discussed, those signatures are ambiguous and difficult to interpret. Here's another angle to consider. What if intelligence has evolved multiple times on Earth? What if it's not as rare as we think? What if the filters that prevent intelligence from leading to detectable civilization are not in evolution, but in sustainability? Think about it this way. Evolution had 4 billion years to produce intelligence. It took 3.5 billion of those years to get from single cells to complex animals. But once complex animals existed, intelligence appeared multiple times independently. Octopuses, with their completely different nervous system architecture from vertebrates, evolved intelligence. Birds evolved it. Mammals evolved it multiple times in different lineages. Primates, dolphins, elephants, even some fish species show signs of complex cognition. Intelligence, once the basic machinery of complex nervous systems exists, seems to evolve readily when it's advantageous. But sustainable civilization? That might be much harder. Human civilization has existed for 10,000 years. Industrial civilization for 250 years. We've come remarkably close to destroying ourselves multiple times. Nuclear war during the Cold War, environmental collapse from pollution and climate change, pandemics, resource depletion, biodiversity loss. We're not obviously on a stable trajectory. It's entirely possible that we'll collapse within the next few centuries. Not extinction necessarily, but collapse back to pre-industrial or even pre-agricultural conditions. If that happens, would we rise again? Would we rebuild civilization? Maybe. But maybe not. Much of our current technology depends on easily accessible resources. Surface coal deposits, shallow oil fields, rich metal ores near the surface. We've mined most of those. They're gone. If civilization collapses and we lose the knowledge and infrastructure to access deep resources, could we bootstrap back to an industrial society? Without easy coal, it's much harder to smelt iron. Without iron, it's much harder to build the tools needed to mine deeper coal. You can see the problem. A post-collapse civilization might never regain industrial technology. They might plateau at a medieval or ancient level of development, or they might develop alternative paths we haven't considered. But it wouldn't be easy. So, maybe intelligence has evolved multiple times on Earth. Maybe some of those intelligences even developed early civilizations. But they hit sustainability filters. They collapsed. They went extinct. And after millions of years, we can't detect that they ever existed. This is deeply speculative, obviously. We have no evidence for it. But it fits the pattern of what we observe. Intelligence appearing multiple times, but only one species currently having civilization. And that one species, us, appearing remarkably fragile. Let's think about the implications of all this. If the Silurian hypothesis is correct, if ancient civilizations could have existed and we simply can't detect them, what does that tell us? First, it tells us something about the search for extraterrestrial intelligence. We look for civilizations by searching for their radio signals, their megastructures, their atmospheric signatures. But what if those signatures only last for a brief window? What if civilizations typically exist for 10,000 years, 100,000 years, maybe 1,000,000 years, and then collapse or go extinct? Let's think carefully about this, because it has profound implications for whether we'll ever detect alien civilizations. The search for extraterrestrial intelligence, SETI, has been going on since 1960 when Frank Drake conducted Project Ozma, pointing a radio telescope at nearby stars and listening for signals. Since then, we've gotten much more sophisticated. We scan billions of channels simultaneously. We look at millions of stars. We search for different kinds of signals, narrow-band transmissions, pulsed signals, broadband noise that might indicate industrial activity. And we've found nothing. No confirmed alien signals. Just a few tantalizing false alarms that turned out to be interference or natural phenomena. This negative result is puzzling because the universe should be full of civilizations if life is common. There are about 200 billion stars in the Milky Way. Most of them have planets. We know this now from the Kepler Space Telescope and other surveys. Many of those planets are in the habitable zone, the range of distances from their star where liquid water can exist. If even a tiny fraction of habitable planets develop life, and a tiny fraction of those develop intelligent life, and a tiny fraction of those develop technological civilizations, there should still be thousands or millions of civilizations in our galaxy alone. But we don't see them. We don't hear their radio signals. We don't see their city lights or waste heat or pollution in planetary atmospheres. We don't see evidence of stellar engineering, Dyson spheres, or swarms capturing a star's energy. This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950, "Where is everybody?" Many proposed solutions to the Fermi paradox focus on why civilizations might be rare. Maybe life is hard to start. Maybe the jump from simple to complex cells is extremely unlikely. Maybe intelligence is a rare adaptation. Maybe technological civilizations self-destruct. But the Silurian hypothesis suggests a different solution. Maybe civilizations aren't rare. Maybe they're common. But maybe they don't last long enough for us to detect them. Think about it this way. Human civilization has been radio loud, transmitting signals into space for about 100 years. We started with radio in the 1890s, but most of that was low power and wouldn't have been detectable at interstellar distances. Television broadcasts, starting in the 1930s, were stronger. Military radar, in the 1940s and 50s, was even stronger. So let's say we've been truly detectable for about 80 years. Now, there's a good chance we won't stay radio loud much longer. We're already shifting away from broadcast television and radio toward cable, fiber optics, and satellite communications. These are directional or shielded, not radiating omnidirectionally into space. Within another 50 years, Earth might be radio quiet again, at least from accidental transmissions. We might still send deliberate signals to other stars, but those would be targeted and intermittent, not the constant background noise we're producing now. So, our radio loud period might only last about 150 years. Less than 2 centuries. If that's typical for civilizations, if the radio loud period is just a brief transitional phase between pre-industrial silence and post-industrial quietness, then the chance of 2 civilizations being radio loud at the same time, close enough to detect each other, becomes vanishingly small. Let's do the math. The Milky Way is about 13 billion years old. Stars have been forming Earth-like planets for maybe 10 billion years. Let's say there have been 1 million technological civilizations in the galaxy over that time. That sounds like a lot. Each civilization is radio loud for 150 years. The total radio loud time is 1 million civilizations times 150 years, which equals 150 million years. But that's spread over 10 billion years of galactic history. At any given moment, the number of radio-loud civilizations is 150 million divided by 10 billion, which equals 0.015. Less than 2/100ths of a civilization, meaning that on average, there's a radio-loud civilization in the galaxy every 67 million years or so. The last one might have been 60 million years ago. The next one might be 7 million years from now. We're incredibly unlikely to overlap with them. And this assumes that civilizations last for at least 150 years, long enough to have a radio loud period. But what if many civilizations collapse before reaching that point? What if only a fraction of civilizations survive long enough to develop radio technology? Then the numbers get even worse. This is one possible solution to the Fermi paradox. Civilizations exist, but they're spread out in time in such a way that they almost never overlap. The galaxy could have been teeming with life and intelligence throughout its history, but at any given moment, there might be no one to talk to. You're alone, not because intelligence is rare, but because it's ephemeral. The Silurian Hypothesis adds another layer to this. Not only might civilizations be separated in time, but even if they overlap, they might not recognize each other, because the traces left by dead civilizations are subtle and ambiguous. Imagine an alien civilization develops astronomy. They build telescopes. They study other planets. They examine Earth. They see an oxygen-rich atmosphere. They see vegetation, though they can't resolve it in detail. They see oceans, continents, ice caps. They see weather patterns. All of this tells them Earth has life. The oxygen alone is a strong biosignature, because oxygen is reactive and shouldn't persist in an atmosphere without constant biological production. But do they see signs of civilization? If they're looking at Earth today, maybe. They might detect narrow-band radio emissions, They might see artificial lights on the night side. They might detect chlorofluorocarbons in the atmosphere, industrial chemicals that don't occur naturally. But if they're looking at Earth 10 million years in the future, after human civilization has collapsed and been erased, what do they see? Just a planet with life. Oxygen, atmosphere, vegetation, oceans. No signs of intelligence. They'd conclude, interesting planet, has life, but nothing technological. Let's look elsewhere. They'd never know that a civilization existed here, and the same could be true in reverse. We could be looking at planets that once hosted civilizations and not recognizing them. We've found thousands of exoplanets. Some are rocky and Earth-sized. Some are in their star's habitable zone. We can measure their masses, their orbital periods, their stars' properties. With advanced telescopes like James Webb, we can start analyzing their atmospheres, looking for biosignatures like oxygen and methane. But we're not looking for technosignatures from extinct civilizations. We wouldn't know what to look for. If a planet shows oxygen and methane, we think, great, possible life. We don't think, could be a dead industrial civilization whose atmospheric pollution has decayed over millions of years into these gases. We're not trained to think that way, so we could be surrounded by dead civilizations and not know it. The Silurian Hypothesis fundamentally changes how we should approach the search for extraterrestrial intelligence. Instead of just looking for active civilizations, we should also look for traces of dead ones. What might those traces look like? Atmospheric anomalies that can't be explained by biology alone. Unusual ratios of isotopes in atmospheric gases. Concentrations of synthetic molecules that shouldn't exist naturally. Though identifying what's synthetic on an alien planet is tricky. Surface features that suggest past industrial activity. Patterns of metal deposition that look artificial. Geometric structures that are too regular to be natural, though detecting these on a distant planet is far beyond our current capabilities. Orbital debris. If a civilization developed space technology, they might have left satellites, space stations, or other structures in orbit. These would decay eventually, dropping into the atmosphere or drifting away, but they might last for millions of years if they're in stable orbits. Of course, detecting any of this from many light years away is extraordinarily difficult. We can barely detect exoplanet atmospheres at all, let alone subtle chemical anomalies. But as our technology improves, as we build larger telescopes and more sensitive spectrometers, we might reach the point where we can search for these markers. And if we find them, it would revolutionize our understanding of life in the universe. It would tell us that intelligence is common enough to have arisen multiple times. But it would also tell us that civilizations are fragile, that they don't last long. That would be both encouraging and terrifying. Encouraging because it means we're not alone. That intelligence emerges, given enough time and the right conditions. Terrifying because it means the obstacles to long-term survival are real and substantial, that most civilizations don't make it. Which brings us to the Great Filter. Second, it tells us something about the Great Filter. The Great Filter is a concept in discussions of the Fermi paradox. The Fermi paradox asks, if the universe is so large and so old, why don't we see evidence of alien civilizations? One possible answer is the Great Filter. Somewhere in the progression from non-life to spacefaring civilization, there's a step that almost no one makes it past. A filter that eliminates most or all civilizations. The question is, where is the filter? Is it behind us? In the step from chemistry to life? or from single cells to complex cells, or from complex life to intelligence? If so, we're lucky to have made it this far, and we might be alone, or nearly alone, in the universe. Or is the filter ahead of us? Is it in the step from industrial civilization to stable, long-term, sustainable, spacefaring civilization? If so, we're in danger. We might be approaching the filter right now. The Silurian Hypothesis suggests the filter might be in sustainability. Intelligence might be common. Civilization might be common. But long-term, survival might be rare. Let's explore this in depth because it's one of the most important questions facing humanity. Robin Hanson, the economist who formalized the Great Filter concept in 1996, argued that the filter must exist somewhere. The logic is simple. The universe is enormous. The Milky Way alone has 200 billion stars. The observable universe has 2 trillion galaxies. That's something like 10 to the 24 power planets, 10 trillion trillion. Even if only 1 in a billion planets develops life, that's still 10 to the 15 power living planets. A quadrillion. Even if only 1 in a billion of those develops intelligence, that's still 1 million intelligent civilizations in the observable universe. But we don't see any. We don't see their radio signals. We don't see their megastructures. We don't see their probes visiting us. So something must be filtering out civilizations. Something must be very hard. So hard that it almost never happens. The question is, what? There are several possibilities for where the filter might be. First filter, the origin of life. Maybe going from chemistry to self-replicating molecules is incredibly unlikely. We've never created life in a laboratory, despite decades of trying. We don't fully understand how it happened on Earth. Maybe it required such an improbable chain of events that Earth is one of the only planets where it occurred. If this is the filter, then we've already passed it. We're safe. But we're also probably alone. Second filter. The emergence of complex cells. For about 2 billion years, Earth had only prokaryotes, simple cells without nuclei. Then, about 1.8 billion years ago, eukaryotic cells emerged. Complex cells with nuclei, mitochondria, organized internal structures. This might have been a one-time fluke, an unlikely merger between different cell types that happened to create a functional whole. If so, then complex life is rare. Most planets might have microbes, but nothing more complex. Again, if this is the filter, we've passed it and we're probably alone. Third filter. The emergence of intelligence. Complex life existed on Earth for over 500 million years before anything resembling human intelligence appeared. Most complex organisms never evolve high intelligence. It's not obviously advantageous for most species. Maybe intelligence is a rare adaptation that only emerges under very specific conditions. Maybe we got lucky. If this is the filter, we've passed it. But there might be other complex life-bearing planets out there, covered in alien equivalents of ferns and trilobites. Just no one smart enough to build radio telescopes. Fourth filter. The development of technology. Intelligence alone doesn't guarantee technology. Dolphins are intelligent, but can't build tools because they don't have hands. Octopuses are intelligent, but are solitary and short-lived, so knowledge doesn't accumulate culturally. Maybe most intelligent species hit some anatomical or environmental limitation that prevents them from developing technology. If this is the filter, we've passed it. But again, we might be alone in having made it this far. Now, all of these filters are behind us. We've already passed them. If one of them is the great filter, that's good news for us, because it means the hard part is over. But it's bad news for the search for extraterrestrial intelligence, because it means we're probably alone. The scary possibility is that the great filter is ahead of us. Fifth filter: the transition from industrial civilization to sustainable civilization. Maybe most civilizations reach the point we're at now: industrial technology, nuclear weapons, fossil fuel dependence, global environmental impact, and then they collapse. Maybe they deplete their resources. Maybe they trigger runaway climate change. Maybe they destroy themselves in nuclear war. Maybe they create some technology that goes wrong: artificial intelligence, nanotechnology, synthetic biology. The result is the same. The civilization ends before it can spread beyond its home planet. If this is the great filter, then we're in serious danger. We haven't passed it yet. We're approaching it right now. And most civilizations don't make it through. The Silurian Hypothesis lends support to this possibility. If ancient civilizations existed on Earth and collapsed, that's evidence that the sustainability filter is real. It means intelligence and civilization can emerge, but they're not stable. They rise and fall. And if that's happened on Earth, potentially multiple times, it's probably happening throughout the universe. Civilizations arise. Number 2, they develop technology. They exploit their environment. They grow rapidly. Then they hit limits: resource depletion, waste accumulation, climate change. They collapse. And a few million years later, all evidence is gone. The planet looks pristine again, ready for the next attempt. This is a deeply unsettling vision. It suggests that the universe might be full of intelligent life, but that intelligence is ephemeral. Civilizations flicker into existence, burn bright for a few thousand years, and then vanish. The galaxy is full of ghosts. Planets that once had cities and art and science, now empty and quiet. And we might be next. Unless we figure out how to pass through the filter. What would that take? Sustainability. We'd need to develop technologies and social systems that can last not just centuries, but millions of years. We'd need to transition from exploiting resources to maintaining them. From growth-based economics to steady-state or circular economics. From fossil fuels to renewable energy. From waste-producing industry to closed-loop manufacturing. We'd need to stabilize our population. We'd need to protect biodiversity. We'd need to avoid nuclear war, engineered pandemics, runaway AI, and whatever other existential risks we create. And we'd need to do all of this before we deplete the easy resources we've relied on. Because if we collapse, if we fall back to pre-industrial or even pre-agricultural conditions, we might not get another chance. The easy coal is gone, mined during the Industrial Revolution. The easy oil is depleting. The rich metal ores near the surface have been extracted. A civilization recovering from collapse wouldn't have access to those resources. They'd have to go deeper, work harder, use more sophisticated technology just to get basic materials. But to develop that sophisticated technology, they need the basic materials. It's a catch-22. So, if we fail now, this might be Earth's only shot at a technological spacefaring civilization. Maybe that's why we don't see aliens. Maybe most planets get one chance. Most civilizations blow it. The planets go quiet again. And the few civilizations that do make it through, that achieve sustainability, become something we can't recognize. Maybe they transcend biology, uploading into computers or becoming something entirely non-material. Maybe they retreat into virtual reality, no longer interested in the physical universe. Maybe they spread quietly, avoiding detection, hiding their presence. Or maybe they're just so different from us, having evolved on alien planets with alien biologies and alien psychologies, that we wouldn't recognize them even if we encountered them. The point is, the Great Filter might be very real, and the Silurian Hypothesis suggests that it's located right where we are now, in the transition from growth to sustainability. That's terrifying, but it's also, in a strange way, hopeful. Because it means that if we can just figure out how to live sustainably, if we can manage our population and resources and technology wisely, if we can avoid destroying ourselves, then we pass through the filter. We become one of the rare civilizations that makes it. And maybe, eventually, we spread to other worlds. We become a multi-planetary species. We establish backups so that if Earth suffers some catastrophe, humanity continues elsewhere. That's how you beat the filter. Redundancy. Multiple planets, multiple habitats, spreading the risk, so that if one civilization falls, others continue. The challenge is getting to that point before we collapse. We're in a race between our technology and our wisdom, between our ability to create powerful tools and our ability to use them responsibly. The Silurian Hypothesis reminds us that this race has been run before, possibly many times, on this very planet. And we don't know if anyone won, but we're about to find out if we can. Third, it tells us something about ourselves. We think of human civilization as permanent. We build monuments meant to last forever. We preserve knowledge in libraries, databases, monuments. We think we're making a permanent mark on the world, but we're not. We're ephemeral. Our cities will crumble. Our knowledge will be lost. Our species might go extinct. And a few million years later, there will be almost no evidence we ever existed. That's humbling. It forces us to confront our own fragility and insignificance. But it's also, in a strange way, liberating. It reminds us that what matters isn't leaving monuments. What matters is what we do while we're here. How we treat each other. How we treat the planet. Whether we build something sustainable or just burn through resources and collapse. Let's sit with this for a moment, because it's profound. We're taught from childhood that we can make a lasting impact, that our achievements will outlive us, that we can be remembered. We name buildings after people. We put up statues. We create foundations and scholarships and prizes bearing someone's name. We write books, hoping they'll be read for centuries. We create art, hoping it will endure. And on human timescales, this works. Shakespeare died over 400 years ago, but we still read his plays. The pyramids were built 4,500 years ago, and they still stand. Plato's philosophy is still studied 2,400 years after his death. These feel like immortality. Like these people and their works have escaped the normal cycle of forgetting. But on geological timescales, none of it matters. In 10 million years, there will be no trace of Shakespeare. His plays will be gone. Not even dust. The English language will be gone. The culture that valued his work will be gone. The pyramids will be gone, weathered to nothing by wind and rain and time. Even if they somehow survived the erosion, the movement of tectonic plates would eventually scatter their stones. Plato's ideas, transmitted through countless copies of manuscripts, will be lost when the last library burns or floods or simply decays. Everything we consider permanent is temporary, and that's hard to accept. It goes against our instincts. We want to matter. We want to last. We want to believe that what we do has meaning beyond our brief lifespans. But the Silurian hypothesis suggests otherwise. It suggests that even civilizations, even entire species, can vanish so completely that later inhabitants of the planet don't even know they existed. If that doesn't make you feel small and insignificant, I don't know what will. But here's the thing: insignificant doesn't mean meaningless. Just because we won't last forever doesn't mean what we do doesn't matter. It matters to us, right now. It matters to the people we affect. It matters to the ecosystems we impact. A civilization that lasts 100,000 years and then vanishes might not leave fossils, but during those 100,000 years, billions of individuals lived their lives. They loved and laughed and struggled and created. They experienced joy and sorrow and wonder and fear. That matters, not in some cosmic, eternal sense, but in the immediate, visceral, human sense. The Silurian hypothesis doesn't tell us that our lives are meaningless. It tells us that meaning isn't about permanence. Meaning is about the present moment and the immediate future, about the lives we touch and the world we inhabit right now. If we're going to be forgotten in a few million years anyway, then we're free. Free from the pressure to be eternal. Free to focus on what actually matters, making things better for ourselves and others while we're here. This is a kind of existentialism. The recognition that there's no inherent meaning imposed from outside, no cosmic scorekeeping, no permanent record that will judge us. We create our own meaning through our choices and actions. And that meaning is real and valid, even if it's temporary. Maybe especially because it's temporary. The Silurian hypothesis also forces us to think about what kind of legacy we want to leave. Not in the sense of monuments or written records, because those won't last, but in the sense of the state of the planet. The only legacy that might survive for millions of years is environmental, the chemistry we change, the species we drive extinct, the materials we concentrate in strange places. That's what future civilizations, whether evolved from Earth's lineages or visiting from elsewhere, might find. They won't find our books or our buildings. They'll find our carbon spike. They'll find our plastic residue. They'll find our 6th mass extinction event. Is that the legacy we want? Or can we do better? Can we transition to a sustainable civilization, one that doesn't just take from the Earth but maintains it, one that protects biodiversity rather than destroying it, one that leaves the planet in better condition than we found it? That's a much harder challenge than building monuments. Monuments are easy. You just pile up stones or pour concrete. Sustainability is hard. It requires fundamentally changing how we relate to resources, to each other, to other species, to the planet. It requires thinking on timescales beyond our own lifetimes, beyond our civilization's lifespan. Thinking about what the planet will be like after we're gone. And the Silurian hypothesis tells us this is possible. If ancient civilizations collapsed due to unsustainability, that's evidence that the default path is collapse. But it also means there's a path that doesn't lead to collapse. The sustainable path. We just need to find it, and we need to find it soon. Because the clock is ticking. We're depleting resources, destabilizing the climate, driving species extinct, all at accelerating rates. The window for transition might be narrow, maybe a few centuries, maybe less. If we wait too long, if we use up too many irreplaceable resources or damage too many critical systems, the transition becomes impossible. We lock ourselves into collapse. So the question isn't just, what legacy will we leave? The question is, will we leave a habitable planet? Will the Earth after us still be capable of supporting complex life? Or will we damage it so badly that recovery takes millions of years? The geological record shows that Earth is resilient. It's survived massive asteroid impacts, supervolcano eruptions, complete glaciation. It's recovered from mass extinctions that killed 96% of species. But recovery takes time, millions of years. If we cause a mass extinction through habitat destruction, pollution, and climate change, the planet will eventually recover. Life will adapt and diversify again. But not on any timescale that matters to us or our descendants. So the legacy question becomes practical. Not, how will we be remembered? But, what will we leave behind? And the answer, right now, isn't great. We're on track to leave behind a warmer planet with higher sea levels, acidified oceans, depleted resources, and drastically reduced biodiversity. A planet that will recover eventually, but that won't support human civilization in its current form. That's a failure, not a cosmic failure, because the universe doesn't care. But a human failure, a failure to be wise stewards of the only planet we have. The Silurian Hypothesis holds up a mirror. It shows us what we might become. Another anomaly in the geological record. Another carbon spike that future geologists puzzle over. Another failed experiment in intelligence. But it also shows us that the outcome isn't predetermined. We have choices. We can continue on the current path and collapse, or we can change course and build something sustainable. The filter isn't inevitable. It's just very, very difficult. And most civilizations, perhaps, don't have the wisdom or the will to pass through it. But maybe we can. Maybe we can be the civilization that figures it out. That makes the transition. That survives. Not because we're special or chosen or destined, but because we're smart enough and cooperative enough and lucky enough to thread the needle, to navigate between the Scylla of resource depletion and the Charybdis of environmental collapse. To build a civilization that doesn't just last thousands of years, but millions. Long enough that our mark on the planet is more than just a chemical signature. Long enough that we might spread to other worlds and become truly difficult to erase. That's the challenge. And the Silurian Hypothesis reminds us that it's a real challenge. Not hypothetical, not distant. Real and immediate. Because other civilizations, possibly, have failed it. Right here, on this planet. They rose. They built. They fell. And now, they're gone so completely, we can barely detect they existed. We don't want to be next. So, we need to learn from the possibility. We need to take seriously the idea that civilizations can fail. That intelligence doesn't guarantee survival, that the default outcome might be collapse. And we need to work, actively and urgently, to be the exception, to be the civilization that breaks the pattern. The Silurian Hypothesis isn't just an academic exercise. It's a warning. Listen to it. The Silurian Hypothesis asks us to think on geological timescales, to imagine ourselves not as the pinnacle of Earth's history, but as one brief chapter in a story that's been unfolding for billions of years. A chapter that might not even be the first. Now, let's address the obvious objection. If ancient civilizations existed, even if we can't find their cities, wouldn't we find something? Some artifact, some structure, some undeniable proof? The answer is probably not. Consider the oldest human artifacts we have. Stone tools from about 3.3 million years ago. Stone survives because it's already rock. It doesn't decay. But even stone tools, after millions of years of erosion and geological processing, become unrecognizable. You couldn't tell a shaped stone from a naturally fractured one. The oldest known structures, like Göbekli Tepe in Turkey, are about 11,000 years old. They're mostly buried. If they'd been on the surface for another few thousand years, erosion would have reduced them to piles of rubble, indistinguishable from natural rock formations. Metal corrodes completely within thousands of years, if not protected. Gold can last longer because it doesn't oxidize, but even gold objects would be worn smooth by erosion, scattered by geological processes, buried so deep we'd never find them. Glass melts back into silica. Plastic degrades. Concrete crumbles. Wood and paper and fabric rot to nothing. The only artifacts that might survive are things buried deep underground in very stable environments. And even those would be altered beyond recognition by heat and pressure over millions of years. So no, we wouldn't find artifacts. We might not even find fossils of the species themselves if they were rare or existed in environments where fossilization is unlikely. The only traces that might survive are chemical signatures, and those are precisely what the Silurian hypothesis tells us to look for. Anomalies in the carbon cycle, unusual isotope ratios, metal concentration spikes, rapid changes in biodiversity. These are subtle, they're ambiguous, they could have natural causes, but they're all we've got. So let me bring this back to Earth, literally. Are there any anomalies in the geological record that could potentially indicate ancient civilizations? Yes, several. And the more you look, the more unsettling the patterns become. Let's go through them chronologically, starting with the most recent and working backward. The Paleocene-Eocene thermal maximum, 56 million years ago. Rapid global warming. Massive carbon dioxide release. Ocean acidification. But we have a natural explanation: volcanic activity and methane release. We've talked about this one already. It's the most commonly cited example because it's well studied and the signatures are clear. But let's dig deeper into what actually happened. The warming occurred in pulses. Not a smooth, continuous increase, but several distinct warming events over about 170,000 years. The main event, the core of the PETM, the Paleocene-Eocene thermal maximum, happened over about 20,000 years. That's fast. Geologically, incredibly fast. To put it in perspective, the current anthropogenic warming has occurred over about 250 years. We're warming the planet about 100 times faster than the PETM did. But the PETM is still much faster than typical natural climate variations, which usually occur over hundreds of thousands to millions of years. The carbon isotope excursion, the shift toward lighter carbon, was about 3 to 4 per mil. That's a large shift, indicating that massive amounts of isotopically light carbon entered the atmosphere and ocean. Estimates suggest that about 4,500 to 12,000 gigatons of carbon were released. For comparison, human civilization has released about 450 gigatons of carbon since the Industrial Revolution. So the PETM released 10 to 30 times more carbon than we have so far. But it took 20,000 years to do it, so the rate of release was much slower. The consequences were severe. Global temperatures rose by 5 to 8 degrees Celsius. The Arctic and Antarctic became ice-free. Tropical forests extended to high latitudes. Ocean acidification caused a crisis in carbonate-producing organisms. Deep ocean anoxia led to mass extinction of bottom-dwelling species. On land, mammals underwent rapid evolution and migration. New species appeared, adapted to the warmer conditions. Some lineages, the early ancestors of horses, primates, and other groups, originated or diversified during this time. The warming lasted about 170,000 years before the climate system began to recover. Carbon was slowly removed from the atmosphere by weathering of rocks, which consumes carbon dioxide, and by burial of organic matter in sediments. The recovery took about 200,000 years. So the total duration of the event, from onset to return to baseline, was maybe 350 to 400,000 years. That's a long time by human standards, but it's a blink geologically. Now, the volcanic explanation for the PETM involves the North Atlantic Igneous Province. This was a period of intense volcanic activity as Greenland separated from Europe and the Atlantic Ocean widened. Flood basalts erupted. Magma intruded into sediments. When magma intrudes into organic-rich sediments, it heats them, causing them to release their carbon as carbon dioxide and methane. This is called contact metamorphism, and it can release enormous amounts of carbon very quickly. The math works. The volume of magma, the area of sediments intruded, the carbon content of those sediments. It all adds up to about the right amount of carbon to explain the PETM. Plus, we can see the volcanic rocks. Thick sequences of basalt in East Greenland, the British Isles, the Faroe Islands. These are the physical evidence of the volcanic activity. So the volcanic explanation is solid. It's well supported. But, and here's where the Silurian hypothesis comes in, how different would it look if the carbon came from an industrial civilization instead? Industrial carbon dioxide from burning fossil fuels would have the same isotopic signature as volcanic carbon dioxide from baking organic sediments. Both are isotopically light. Industrial warming would affect the same systems. Ocean acidification. Check. Deep ocean anoxia. Check. Terrestrial warming and ecological disruption. Check. The rate of release is actually the main difference. Industrial release is faster. But if an ancient civilization collapsed, if their technology failed or their resources ran out, the release would slow or stop. The geological record would show a rapid pulse of carbon release followed by slower background release as the planet's natural systems responded, which is exactly what we see in the PETM. Now, I'm not saying the PETM was caused by an ancient civilization. The volcanic explanation is good and fits the evidence. I'm saying we couldn't easily tell the difference. Not after 56 million years. Not with the evidence we have. Let's look at another event. The Toarcian Oceanic Anoxic event, 183 million years ago, during the Jurassic period. This was a major extinction event, particularly affecting marine life. About 20% of marine families went extinct. The pattern is familiar. Rapid global warming, about 7 to 10 degrees Celsius. Ocean acidification, widespread anoxia in deep and even shallow marine environments. Carbon isotope excursion indicating massive carbon release. Disruption of the carbon cycle lasting about 300,000 to 600,000 years. The proposed mechanism is, once again, large igneous province volcanism. This time, it's the Karoo-Ferrar province, volcanic activity associated with the breakup of Gondwana, the southern supercontinent. Magma intruded into coal seams in southern Africa, baking them and releasing carbon. The scale of volcanism was enormous, covering an area larger than Western Europe. Again, we have the physical evidence. Basalt flows, volcanic ash layers, dikes and sills where magma intruded into sedimentary rocks. The volcanic explanation fits. But the signatures are the same as we'd expect from industrial activity. Rapid carbon release, ocean acidification, warming, extinction. The event occurred during the time of the dinosaurs, about 60 million years after they first appeared. If an intelligent dinosaur species had evolved, developed industry, and collapsed, this is what it might look like. Again, I'm not claiming that's what happened. I'm pointing out the ambiguity. Let's go further back. The Permian-Triassic extinction, 252 million years ago. This is the big one, the worst mass extinction in Earth's history. About 96% of all marine species went extinct. 70% of terrestrial vertebrate species. It's called the Great Dying. The proximate cause appears to be the Siberian Traps, the largest volcanic event in the last 500 million years. Flood basalts covered an area the size of Europe. The eruptions lasted for about 1 million years, though the main pulse occurred over about 60,000 years. The environmental consequences were catastrophic. Massive carbon dioxide release caused extreme global warming, maybe 10 to 15 degrees Celsius. Ocean acidification destroyed carbonate producers. The oceans became anoxic and sulfidic, filled with hydrogen sulfide produced by bacteria in the oxygen, poor, deep water. Hydrogen sulfide rose to the surface and even entered the atmosphere, poisoning terrestrial ecosystems. The ozone layer was damaged, allowing harmful UV radiation, ultraviolet radiation, to reach the surface. Acid rain from sulfur dioxide devastated what was left of terrestrial life. It took 5 to 10 million years for ecosystems to recover. The extinction was so severe that it reset the evolution of life on Earth. The Permian world was dominated by synapsids, the group that eventually gave rise to mammals. The Triassic world was dominated by archosaurs, the group that gave rise to dinosaurs and crocodiles. Everything changed. Now, the Siberian Traps volcanic explanation is extremely well supported. We can see the basalts. We can date them precisely using radiometric techniques. They're the right age. They're the right chemical composition. We can calculate how much carbon dioxide they would have released. It all fits. But here's a thought experiment. If a civilization existed 252 million years ago, if they had advanced industrial technology, if they collapsed in a cascade of environmental disasters triggered by their carbon emissions, what would we see? Extreme warming, check. Ocean acidification, check. Anoxia, check. Mass extinction, check. Collapse of ecosystems, check. Prolonged recovery period, check. The only definitive difference is the volcanic rocks. Industrial activity wouldn't create basalt flows. But what if the volcanic activity and a civilization's collapse happened at the same time? What if the Siberian Traps erupted? and that triggered climate change that pushed a marginal civilization over the edge. Or what if industrial activity triggered volcanism by destabilizing the crust? Deep mining, fracking, underground nuclear tests. These activities can induce earthquakes and potentially trigger volcanic activity if the magma is already close to the surface. This is speculation, obviously. Wild speculation. But the point is, once you start looking for alternative explanations, you realize how ambiguous the evidence is. Let's consider one more event, this time going much further back. The Great Oxidation Event, about 2.4 billion years ago. This wasn't a sudden catastrophe. It was a slow transformation that took place over several 100 million years. But it fundamentally changed the planet. Before the Great Oxidation Event, Earth's atmosphere contained almost no oxygen. Life existed, but it was all anaerobic, living without oxygen. Photosynthetic bacteria, specifically cyanobacteria, had evolved by about 3 billion years ago. They used sunlight to split water molecules and release oxygen as a waste product. But the oxygen didn't accumulate in the atmosphere. It reacted with dissolved iron in the oceans, forming iron oxide that precipitated to the ocean floor. This created the banded iron formations, layers of iron-rich rock that we mine for iron ore today. Eventually, all the dissolved iron was used up. The oxygen sinks were saturated, and oxygen began to accumulate in the atmosphere. This triggered the Great Oxidation Event. Atmospheric oxygen rose from nearly zero to maybe 1 to 10% of current levels. The consequences were profound. Methane, a greenhouse gas that had kept the planet warm, reacted with oxygen and was removed from the atmosphere. The planet cooled dramatically, possibly triggering a global glaciation, the Huronian glaciation, which may have covered the entire planet in ice. This is sometimes called snowball Earth. Anaerobic organisms, which found oxygen toxic, were driven to extinction or forced into oxygen-poor environments like deep sediments and the guts of animals. Aerobic organisms, which could use oxygen for metabolism, gained a huge advantage. They could extract much more energy from food than anaerobic organisms. This set the stage for the evolution of complex life. You can't have complex multicellular life without oxygen. The energy demands are too high. So, the Great Oxidation Event was, in a very real sense, the precondition for everything that came after. Without it, we wouldn't be here. Now, the standard explanation is that this was entirely biological. Cyanobacteria evolved. They photosynthesized. They produced oxygen. The oxygen accumulated once the iron sinks were saturated. End of story. But here's a question. Why did it take so long? Cyanobacteria evolved about 3 billion years ago. The Great Oxidation Event happened about 2.4 billion years ago. That's a gap of 600 million years. Why did oxygen suddenly start accumulating after 600 million years of cyanobacteria pumping it out? The usual answer is that something changed in the balance between oxygen production and oxygen consumption. Maybe tectonic activity slowed, reducing the supply of fresh iron to the oceans. Maybe volcanic activity decreased, reducing the amount of reducing gases like hydrogen sulfide and methane entering the atmosphere. Maybe biological oxygen production increased for some reason. These are all plausible. But what if something else happened? What if a civilization existed during that 600 million year gap? This is really wild speculation now. We're talking about a civilization existing more than 2 billion years ago, before complex life. before eukaryotic cells even existed. It seems absurd. But let's think about it. If single-celled organisms had evolved intelligence somehow, if they had found a way to cooperate and form multicellular structures, if they had developed technology based on biochemistry rather than metals and fire, what traces would they leave? They wouldn't build stone cities. They wouldn't smelt metals. They wouldn't burn fossil fuels because complex organic deposits wouldn't exist yet. But they might manipulate their environment in ways that affected global biogeochemistry. They might cultivate photosynthetic bacteria to produce more oxygen, or suppress them to keep oxygen low. They might mine minerals from the ocean floor for trace elements. They might alter ocean chemistry to favor certain metabolic pathways. The traces would be subtle, changes in isotope ratios, shifts in mineral deposition patterns, unusual layering in rocks. And after 2.4 billion years of plate tectonics, erosion, metamorphism, and geological recycling, almost nothing would remain. I'm not seriously proposing this happened. The idea of an intelligent bacterial civilization is absurd by most reasonable standards. But the point is, when you go back far enough in time, the evidence becomes so degraded that you can't rule anything out with certainty. 2.4 billion years is a long time. Most of the ocean crust from that period has been subducted and recycled. Most of the continental crust has been metamorphosed. The few rocks that survive from that era are heavily altered. If a civilization existed then, we'd never find direct evidence. We might see anomalies in the geochemistry, but we'd explain them with natural processes because that's all we can conceive of. The Silurian Hypothesis forces us to confront this uncertainty. It asks us to acknowledge that our knowledge of Earth's deep history is fragmentary and incomplete. It asks us to consider possibilities that seem absurd but can't be definitively ruled out. And it reminds us that absence of evidence really isn't evidence of absence. Not when you're dealing with timescales, where continents drift across the globe and mountains rise and erode to nothing. Let me be clear, one more time. This doesn't mean ancient civilizations existed. The volcanic explanations are solid. They fit the evidence. There's no compelling reason to invoke ancient civilizations. But the point is, we can't rule them out either. Not definitively. Not with the evidence we currently have. And that's unsettling. Here's one more thought experiment to drive this home. Imagine you're a geologist, 10 million years in the future. Humans are long extinct. Some other species has evolved intelligence and developed geology as a science. They drill a core through sedimentary rock dating to the late Holocene, our current epoch. They analyze the chemistry. They find a spike in carbon dioxide. They find ocean acidification. They find a mass extinction event. They find unusual concentrations of metals and rare earth elements. They find traces of plutonium, though heavily decayed. They find a thin layer saturated with plastic microparticles. What do they conclude? If they're thinking like current geologists, they look for a natural explanation. Volcanic eruption? But there's no volcanic rock layer. Asteroid impact? But there's no iridium spike. No impact crater from that time. Methane release? Possible, but the timing and scale don't quite fit. They might puzzle over it. They might propose various mechanisms. They might eventually settle on some combination of natural processes that mostly fits the data. Or, if they're thinking like Schmidt and Frank, they might consider another possibility. An industrial civilization. One that burned fossil fuels, mined metals, created plastics, split atoms, and then collapsed. The evidence fits, all of it, but they could never prove it, not conclusively. Because civilizations don't leave unambiguous markers on geological timescales. They'd always have just enough doubt to publish their findings as anomalous carbon excursion of unclear origin, possibly related to unusual volcanic activity or destabilization of methane hydrates. And that's exactly where we are now, looking at anomalies in the geological record and explaining them with natural processes, never quite considering that some of them might not be natural at all. So, what's the takeaway from all of this? The Silurian Hypothesis doesn't claim ancient civilizations existed. It asks a different question. If they did exist, would we know? And the answer appears to be, probably not. Our methods for detecting ancient civilizations are inadequate. We rely on finding artifacts. But artifacts don't survive geological timescales. We look for obvious structures, but erosion and plate tectonics erase those. We explain anomalies with natural processes because we're not trained to consider alternatives. This has profound implications. For the search for extraterrestrial intelligence, it suggests we might be looking for the wrong things. Radio signals and megastructures require active civilizations. But if civilizations typically last only a brief time before collapsing, we should be looking for geological signatures instead. Planets with anomalous atmospheric chemistry, unusual isotope ratios in their rocks, signs of past industrial activity rather than current activity. For our understanding of Earth's history, it suggests we might be missing entire chapters. Species that rose to intelligence, built civilizations, and vanished, leaving only ambiguous chemical traces we've misinterpreted. And for our own future, it's a warning. Civilizations are fragile. They don't leave permanent marks. After we're gone, the Earth will erase us with the same indifference it's erased everything else. If we want to matter, if we want to survive, we need to think on longer time scales. We need to build something sustainable, because if we don't, we'll just be another anomaly in the geological record. Another carbon spike that future geologists puzzle over and explain away. Let me end with this thought. Right now, you're sitting on a planet that's 4.54 billion years old. Beneath your feet are rock layers recording most of that history. Those rocks contain stories. Stories of ancient oceans and vanished mountains. Stories of continents that drifted and collided. Stories of species that evolved and went extinct. And maybe, just maybe, some of those rocks contain a different kind of story. A story of intelligence that emerged millions of years before ours. A story of beings who looked up at the stars and wondered about their place in the universe. A story of civilization that rose and fell and left only the faintest traces. We can't prove that story. We might never be able to prove it, but we can't disprove it either. And that uncertainty, that possibility that we're not the first and might not be the last, that everything we think we know about our uniqueness might be wrong, that's what makes the Silurian hypothesis so compelling. It forces us to question our assumptions. It forces us to think bigger, deeper, longer. It forces us to confront the possibility that the Earth has been home to wonders we can barely imagine. And whether or not ancient civilizations actually existed, whether or not we ever find proof, just asking the question changes how we see ourselves. We're not permanent. We're not inevitable. We're not even necessarily first. We're just one species, on one planet, having our brief moment in the sun. What we do with that moment, whether we build something sustainable or burn bright and fade, whether we leave a legacy or just another ambiguous carbon spike, that's up to us. The Earth has been here for billions of years before us. It will be here for billions of years after we're gone. The question is, will anyone remember we were here? Will anyone find our traces and wonder about us the way we wonder about the possibility of those who came before? Or will we, like the hypothetical Silurians, vanish so completely that future intelligences don't even know to look? That's the real question the Silurian hypothesis asks. Not whether ancient civilizations existed, but whether we matter, whether what we build, what we learn, what we accomplish, has any permanence. And the answer, uncomfortable as it is, seems to be no. Not in the way we imagine. Our monuments will crumble. Our knowledge will be lost. Our species will go extinct. The only thing that might survive, the only thing that might hint that we were here, is the state of the planet we leave behind. The climate we altered, the species we drove to extinction, the chemistry we changed. Those will be our legacy. Not our art, or our science, or our technology, but our impact on the Earth's systems. And that's a sobering thought. It means that how we treat the planet, how sustainable we make our civilization, how carefully we manage our resources and our environment, these aren't just practical concerns. They're our only shot at being remembered. If we collapse after destroying the environment, future geologists will see a carbon spike and an extinction event and explain it with volcanism or methane or something. They won't know we existed. But if we build something sustainable, if we last not just thousands, but millions of years, if we spread beyond Earth and establish ourselves across the solar system and beyond, then we have a chance. Then our legacy becomes not just chemistry, but presence. The Silurian hypothesis is ultimately about time, about how brief even the longest civilization is compared to geological time, about how thoroughly the Earth erases history, about how we're all temporary, all ephemeral, all destined to be forgotten, unless we do something remarkable. So here we are, at the end of this journey, having explored the possibility that we're not the first intelligent species Earth has produced, having examined the evidence, or lack thereof, having confronted the unsettling reality that we probably couldn't detect ancient civilizations even if they existed. Where does that leave us? It leaves us with questions. Questions about our place in Earth's long history. Questions about what traces we'll leave. Questions about whether we're unique or just the latest in a long line of intelligences that rose and fell. We don't have answers. We might never have answers. But we have the questions. And sometimes the questions are what matter. They change how we see ourselves. They change what we value. They change how we think about the future. If we might not be the first, then we're not as special as we thought. If we probably won't be the last, then our responsibility is not to ourselves alone, but to whatever comes after. If we're just one chapter in Earth's story, then we'd better make it a good one, because the story continues whether we're here or not. The Earth doesn't care about us. It will spin on, oblivious, for billions more years. What we do while we're here, how we treat the planet, whether we build something sustainable or just another flash of intelligence that burns out, that's our choice. The Silurians, if they existed, made their choice. And now they're gone, erased so thoroughly we can't even prove they were here. What choice will we make? Thanks for staying with me through this long exploration of one of the strangest and most thought-provoking ideas in science. The Silurian hypothesis might never be proven. It might never even be taken seriously by mainstream geology. But it asks the right questions. Questions about evidence and time and legacy. Questions that force us to think beyond our own brief existence. Questions that remind us how small we are and how temporary. And maybe that's exactly what we need to hear.